Okay, well, numbers are still building up slowly, but we'll make a start. So, welcome to another session of Dr. Andrew French, rattling through some of the round one questions of yesteryear. So, it's very important that you get some ideas about how you go about these things, and then you have a go yourself. You have to solve the problem yourself. No good watching somebody else do it. It's like watching a film. It's great entertainment, but if you're going to learn something, do it yourself. So, make sure you pick up some points, um, get an idea of what you're meant to be doing, which is 99% draw a diagram, and then follow what's done, make some notes, but don't sort of feel you've got to copy down exactly what's written here, and then do it yourself in the very near future. Maybe not this evening, but try it tomorrow. Try one or two of the questions tomorrow so that you're able to really just develop your fluency yourself. Okay, well, thank you very much, Dr. French.
Okay, good evening, everybody. Welcome to BPhO training. And if you are new, fantastic. And if you have been coming to all the others, that's even better. So we're going to look at some real paradigm questions from today's paper. So it's not going to be so much mechanics today. We're going to start off with a little bit of kinematics, but we're going to look at some waves and we're going to look at some capacitors. And then if all goes well, we might continue with our cosmic ladder and have a look how Ole Roma worked out the speed of light. So there we go. So stick with it and we can get that. So anyway, Roland, thank you for coming. As Professor Hughes says, the best way for maximum enjoyment, so make some notes on the piece of paper. And even if it's just the how you start. And we've in discussions before, a lot of the questions, the how you go about starting is often the hard bit. For some of these questions, so I think one or two of these are very much of that ilk. All right, okay, let's make a start. So I'm just going to share my screen. Okay, so here we go. So we're going to do M first, which is about some ships. Can I just confirm? Is my screen looking nice and clear?
Yep, it is.
Fantastic. So there we go. So we've got two ships, A and B, spot each other at the moment. Ship B is due south of A with a sort of range in nautical miles. All right, so there we go. We've got bearings and we've got knots. So nautical miles per hour, basically. There we go. So we don't need to convert to anything. So basically what we want is a scale. The distance is in nautical miles and time in hours. So the first thing we want to do is kind of represent this information. So there we go. Ship A is traveling at a bearing of 090 at 5 knots. So basically what you can think about is you want to sort of see, let's find out where they are. So they're initially, it's due south of A. So what we've got is that we've got A and B. So here we go. So there's our starting ships. So there's B and there's A. All right. Okay, so what we've got is it's going at 5 nautical miles per hour and it's at 090. So if that's north, then we're going to be going this far in t seconds. So 5t is how far ship A's gone. Let's have ship B in a different color, shall we? There we go. So ship B. So that's initially 2. All right, so I don't need a unit because we've got all that defined. So we'll go for distances in nautical miles. All right, and we've got times in hours. And that means we can just write down 5t, etc. So the other one was going at 20 knots. That's ship B. So that's ship B here. All right, and so what I'm really trying to do, I'm putting a lot of effort to try and decompress this question, sort of expand it out in terms of a nice picture. So in t seconds, how far has this gone? And this is kind of how you solve a lot of these problems. Let's make sure that looks like it's going a bit further out. There you go. So what's my angle? It's supposed to be 30 degrees. So there we go. Let's have that as 30 degrees. There we go. That's going to be 30 degrees. So that distance there is 20t. We probably ought to have it so it's at a little bit of an angle. So I'm going to increase that a little bit, just up there. There you go. Right. So there we are. So that's 20t. And what we're trying to work out is the distance of closest approach. So if we work out a vector between these two things, let's call that distance r. And the distance of closest approach is probably what we're trying to find. And maybe it might be useful to sort of decompose that into y and x components, because we've got sort of like of natural sort of XY components or north, east kind of components here. So there we go. There's our coordinate system, north and east. All right, so I think that's the right diagram to draw. I think that's got everything in it. And what we're trying to find. So our bearings, of course, is clockwise from north. What do we want? We want the distance of closest approach. That's going to be using Pythagoras. That's how we can work it out. And we can find x and y from our other vectors. So let's go and write that out. So the first thing we might do is we might say, well, r is going to be, well, r squared is x squared plus y squared. That's Pythagoras. So if you're new today for these kind of things, if you can't see your way through the question, which to be honest is probably most of them, they're well designed, just writing down the answer would be a sort of real strike of genius. And actually wouldn't get you all the marks because you need to sort of explain your journey. A lot of it's about stating the problem in a more clear way and writing down what all the connections that you can see. That might be geometrical. It might be a law of physics. In this case, it's just really geometry because we've already put the kinematics in our diagram. So what we need to do is we need now to find x and y in terms of t, in all terms of all the other things. So what might I do? Well, if you think about it, so we've got our, if we resolve our components here, remember we want this sort of closest approach for what we're doing. So what we could say is, well, if in this the way I've put this diagram, 20t cos 30 plus y. If I sort of like put a little dotted line there, you can sort of see the triangle of the sort of low of B's path. And what we can say is, according to this diagram, that 20t cos 30, all right, plus y is going to be 2. Now, you might say, well, what happens when that goes, beyond it? Could we have r going the other way? But that's okay because then, we'll have a sort of negative on these things. So that's not really a problem. Y can be negative if we want. So that's going to be equation 1. And if we look at the sort of x components of this one, 5t plus x is going to be 20t sine 30. So 20t sine 30, right, will be, according to my diagram, x plus 5t. Just check I've got all of that right. Yeah. All right. So there we go. So we've got 3 equations now. And, mathematically, is that sufficient? Let's have a look. So, yes. So basically what we can do is we can use equations 2 and 3 to substitute for x and y. And that will give an equation for r in terms of t. And so basically, if we want the distance of closest approach, then we can take the derivative of r with respect to t, and that will minimize r. All right, so that's the kind of heuristic. That's now our recipe. All right, so let's go and do it. And why does that work? Well, r really is parameterized by time. So we might say right at the start r of t, and what we want to do, we want to find r such that dr by dt is 0. Okay, I suppose technically we want to minimize r rather than maximize it, but it is going to be a minimum. Why? Because of course it's in motion, so that r is only going to get bigger. All right, once we get beyond our minimum here. So I think all we need to do is do that. We don't need to work out the second derivative and set that to be less than 0, that kind of thing. All right, so can I just check, am I coming across all right? Is this loud and clear?
Yes.
Fantastic. So let's go and do it. So firstly, we want to substitute for x and y. So what do we got? So for 3, we've got x is 20t, and now we'll have sine 30 is a half. So let's simplify that, minus 5t. So let's make sure we've got our special triangle here. So 1, there we go. We separate that out. That's 30 degrees as well. So we've got half, and then we've got root 3 on 2. Right, it's cos 30. So what do we got here? We've got 10t minus 5t. So I make that 5t. Okay. Yep. I think that's 5t. So x is 5t. And then what we can do now is let's look at number 2. So what have we got here? We've got y is going to be 2 minus 20t cos 30. So that's going to be 10 root 3. 10 root 3t. I think that's okay. Yeah, so cos 30 is root 3 on 2. We've got 20, so I think that's all good. All right. So if we're doing substitutions, carefully make our simplification, check that we've not made any errors. And therefore, let's just change color. Therefore, what we got, r squared is equal to x squared plus y squared. So that's going to be 5t all squared. And this looks like I'm about to go into an algebra fest now. So I'm going to just check. I'm going to copy my things down, and then I'm going to expand. So just make sure it's getting late. So I'm old, so I might make some mistakes here. So I'm going to just do that very carefully. And let's expand that out. So what do we got? We've got 25t squared plus 4 minus 40 root 3t. And then we've got plus 100 times 3, so 300 t squared. I think that's all good. So what have we got? So 3, 2, I'm just checking my numbers here. So therefore, r squared, I make that 325 t squared. We've got a minus 40 root 3t, and we've got a 4. I think that agrees with what I did last time. Hooray! Okay, now, here's the question. Do we have to square root this? Well, not really, because if dr by dt is 0, then the derivative of r squared with respect to time is 0. And if you are unhappy about that in any way, we could do it implicitly. Now, I'm not sure how many of you will have done this, but basically that's the same as 2r dr by dt. So it's kind of using the chain rule. We're sort of, you could say that z is r squared, all right? So therefore, dz by dt is dz by dr times dr by dt. That's a bit of calculus magic there. So that's what we're kind of doing. So if dr squared by dt is 0, if dr by dt is 0 and r is not 0, then so is dr squared by dt. All right. So let's just write that out. So if dr by dt is 0 and r does not equal 0, this means that dr squared by dt is 0. Okay, fantastic. So we're on mathematically sound footings here. So what we need to do now is find the derivative of r squared with respect to t. It's actually a quadratic. All right, so so r squared will sort of look like a sort of happy mathematician, and our minimum is going to be what we want. So let's go and do it. So dr squared by dt. So we're going to get twice that. So what do we got? We've got 650. We've got minus 40 root 3. And there we go. So therefore, when dr squared by dt is 0, this means that our t is equal to 40 root 3 divided by 650. All right, which is about, if you put it into a calculator, 0.107 hours. Okay. But that's not quite the question, is it? We've got to then find r minimum. Haha, so we have to go and plug that back in. And so again, let's find r squared. So there's many times in physics where the square of something, it's going to be easier to find than the thing itself. I'm just going to scroll that out so you can all see. I hope that's all right. Okay. Yeah, just let me know. I had some feedback last week. Sometimes there's a bit too much scrolling, it's making some of you get motion sickness. So do mention, and my fantastic students will let me know, hopefully, if that is happening. So also, is this too small to see, by the way? Do I need to make this slightly bigger?
Well, it looks okay to me. I mean, I'm looking at a sort of laptop screen. On a phone, it would be small.
All right, I'll see what I can do. So what have we got? So
I,
3,
I
2.
I think it's okay. No complaints so far.
That's all right. So let's go and substitute it. And again, I'm going to do good mathematical hygiene here. I'm just going to substitute what I've got, and I'm going to sort out the maths later. So 40 root 3, and I'm going to put that, so 40 root 3 over 650. And I've got a plus 4. So I'm going to do my substitution first, and then I'm going to sort out the numbers. And you could use a calculator if you want, as you're amazing at arithmetic. That gives you 48 over 13 plus 96 over 13 plus 52 over 13, which is rather lovely. And so what does that give you? That gives you 4/13. 4/13. So therefore, our final answer is r min is 2 over root 13. Oops, not over root 3, sorry, root 13, which is approximately 0.55 nautical miles. that would be the ultimate answer. I think we should try and keep in exact fractions and things like that if we can. But I would have no problem if you're doing this at speed, sticking 0.107 hours into the formula for R squared here. I'm sure you would get all marks for that. There we go. So there we are. I think that's a nice little warm up. A bit of introductory calculus if you're new to that kind of stuff. So what are the key points here? Saying, well, we want to find the distance between where A and B are. So the first thing you want to do is definitely draw a diagram. That then makes sense. It defines what R is. And we want to find how R varies with time. And then it's a case, this is now a calculus problem of finding the derivative of that. And a nice sneaky thing is you can make life easier by doing the derivative of R squared rather than R. And that's just a nice trick, which crops up in all sorts of places. And we know that because of the Pythagoras, which is equation number 1. Okay, any questions? Anything from the chat that's come about? Nope. Am I still broadcasting all right?
Yes.
Fantastic. Good. Yeah. So, okay. So what we're going to do is a very different problem now. So I think we should do a waves problem. We haven't done one of those yet, actually. So let's go and have a little look. I'm just going to scroll this one. Here we go. So a thin wire of mass 6 grams and length 1.2 meters is stretched to a tension T. 2 fixed supports. Well, that's good news. That means we have what kind of wave? Stick that in the chat. What's the magic word?
Stationary wave is the most popular answer coming up.
Yes, I just realized it actually even gives that. Never mind. But yes, a standing wave, stationary wave. There we go. And the third harmonic, etc. Right. So, okay, blah, blah, blah. So in such a way, total kinetic energy and elastic potential energy are equal. Fantastic. Right. We're given a tension. We're given the amplitude. So we want to sketch a graph of the maximum kinetic energy of the particles in the wire against their position. So what we really want to do first is just maybe remind ourselves of what those standing waves are. And then we can kind of go about to find what this kinetic energy is. So it's more of kind of, probably it's the closest thing we've got to kind of bookwork, really, this question, by having some notes. So I think this might be quite a good idea to sort of like just make sure we understand this. So I have a little demonstration for this. If I can just get the right mouse. So you can download all my bits of code from my website. So the Eclecticon, which is the link to this is in the chat, and here's one of them. So this is an app. It may not be quite sophisticated as the ones from the Computational Physics Challenge, but here we go. So what we've got is a standing wave. So I've got this sort of string, and it's represented a snapshot in time. Is this sort of like a green wave here? By the way, I've not actually no, I still am broadcasting good. So what I've got is the sort of colored lines here are representing different times within a wave period. So, if you pluck a guitar string, so I play around with guitars occasionally, and if you look at a guitar string, it sort of follows this this sort of envelope, because you can't see the string is vibrating so fast, the eye can't really track it. So what I'm doing is essentially it's sort of like not a time lapse, but a sort of hyperlapse where I'm plotting the waves all on top of each other. So if I evolve time, you can sort of see my wave moving like this, and it goes backwards and forwards. And it's a standing wave, so it has nodes at either end. That could be nodes of pressure if it's like, say, a flute or something like that. Or let's keep it to a guitar string where the actual string itself is pinned. So what's going on? Well, the nodes quantize our wave, and the quantum I use explicitly here because it's the same kind of thing that we have in quantum mechanics, right? We constrain our wave to have, in this case, a whole number of half wavelengths is the length of our string, which is 1 meter in my case, okay? And so what I've also got are these little observation points. So at, let's go for 0.2, 0.4, and 0.8. So I can move these sliders around. So what I'm looking at here is how does the wave move in time? So at 0.2, you can sort of see, again, a sinusoid or a cosinusoid, and the amplitude of that gets bigger as we get closer to the middle of the wave where my antinode is. So it's this sort of idea where you've got a kind of temporal picture, which is the bottom one, at a particular position, and you've got your sort of how the wave moves, a sort of photograph, which is how it evolves in space, which is the top one. All right. So a standing wave is where essentially you've got a sort of similar phase relationship. What does that mean? Well, at any point, it has the same time variation. Okay, so at any point along this wave, we have the same time variation, but the amplitude of that varies along the wave. So hopefully you can kind of see that by the fact that we're decoupling the time variation and the spatial variation, a standing wave is literally a product of a mathematical product of a sine wave in time and a sine wave in space. Okay, hopefully that kind of makes sense from the picture here, and it kind of makes sense if it's a bit more dynamic. So I find that when I'm teaching this, a lot of confusion sometimes happens about where the phase of a standing wave. I think we just need to sort of spec that out. It means that the time variation is the same all the way along the wave. All right, but the spatial envelope of that function is also cosine or sinusoidally varying. So there we go. So this is the harmonic number 1, which is the we call that the fundamental, and then the first overtone, right, is harmonic number 2, and that one's where we have an extra node in the middle. All right. So there we go. So they're quite good to sketch these things. And if you want to try and sketch it, the trick is to put the nodes first and then draw the envelope. If you don't do that, your wave, well, it's never going to be symmetrical unless, well, I never make it symmetrical unless I do the nodes first. That's like sort of painting by numbers. And there we go. So that's harmonic number 3, second overtone. And now we've got 2 extra nodes. You get the idea. All right. So let's go and draw that in our here we go. And then we can use that to work out the wave displacement and then things like our kinetic energies, etc. All right, so let's go and do this. All right, so let's just scroll that out. So what have we got? So first part, we want to sketch a graph of the maximum kinetic energy. So yeah, we could go straight there, but I think I'm going to work out what our fundamentals are. So here we go. So we've got nodes, right, at both ends of the wire. So our quantization condition, that means L is going to be n lambda over 2, where n belongs to an integer. That's an integer. You've not seen that symbol. Okay, so there we go. So let's go and draw it. And I'm also going to define something for the amplitude, which again, psi, which is what we use in quantum mechanics. So wave mechanics, we're using the same kind of physics. So there we go. There's our envelope. So versus time, and let's go and have a snapshot in time. So 1 moment in time, as the song goes. That's my fundamental. That's L. Okay, so this is called the fundamental. Okay, which is all the first harmonic. And L in this case is going to be lambda over 2. Let's do another one. Let's do the first overtone. So there's psi. All right, these are ends, and we're going to have an extra node. So there we are. That's L. And now let's have it. So we've got our extra node in the middle. Again, these are the various positions. All right, and let's have a snapshot in time. There you go. All right, so I've deliberately done it so it's not in the extreme positions. That's going to be the first overtone. All right, which is the second harmonic. So it's very easy to get confused with overtones and harmonicness. So I think harmonic number is n, basically. So an n is 1, 2, 3, etc. All right, and there we go. So so this one, L, is going to be 2 times lambda over 2. All right, and there we go. So so we can keep going with extra fundamentals, and indeed, you know, for interesting sounds, it's the sum of all those harmonics. We'll see how time goes. I have a little spectrograph. Maybe I'll sing to you or something like that, and we can decompose my voice into its component parts. But let's just solve this problem first. So let's write down a mathematical expression for the wave displacement. So what do we want? We want the wave displacement as a function of x and time. So let's define what we mean by x. Well, how about x being from here? All right, so what's that going to be? It's going to be our maximum amplitude. Let's call that A. And then what we want, we've got a sine wave. You could use cosine if you like, but 2 pi radians times x over lambda. All right, so in one wavelength, we've got a full sine wave. All right, and we're going to multiply that by cos omega t for our standing wave. So omega is going to be 2 pi times the frequency, or 2 pi divided by the period. Okay, so in this little bit here, if you're new to using cosines to model stuff like this, what we've got is a cosine of 2 pi radians, or 360 degrees, times the number of periods. Okay, so that might be sometimes that's a source of confusion too. So in an integer number of periods, we've got cos of 2 pi radians. We go all the way around. So there we go. So that's our sort of our general idea of a standing wave. And then we can use our quantization condition. So the nodes of both ends. So that means, so since what we've got L is n lambda on 2, which means that lambda is 2L on n. What we can do is we can put that all in there. All right. So let's just put that together. So therefore, 2 pi x over lambda, what's that going to be? That's going to be 2 pi x times the reciprocal of that. That's going to be n over 2L. So the 2's cancel. And we have pi n x over L. Yes. Okay. So I'll just zoom out a little bit so you can sort of see those. Therefore, my standing wave formula, I could argue, do we really need to write this down to answer this question? Probably not, but I think we do need, if I'm going to do some mathematics now so I can sketch something properly, I think we kind of need to know where that's come from a little bit. So, so my standing wave, is going to be phi x of t. Sorry, psi, that's my sort of the height of my wave, as it were, is my amplitude times sine, and that's going to be pi n x on L times cos omega t. All right. Right. So how do we use that to work out our potential energy and kinetic energy? So if you actually have a little look here, it sort of says, in such a wire, the total kinetic energy and elastic potential energy are equal. Well, that's jolly good. If we work out the kinetic energy, well, that's going to be to do with the rate of change of displacement. So I would suggest that given the velocity, all right, is upwards, so therefore my velocity is going to be d psi by dt. All right, if you think about my waves, if I just go back to my simulation just a moment. Am I still broadcasting all right, everybody?
Yes.
Fantastic. So if we, let's say, for example, let's see where my mouse pointer is, sort of hovering at the red line. And if I evolve time, you sort of see it's going up and it's going down. So we're not sort of like waterways. We're not making some sort of circular motion here, which is going up and down. So I'm going to argue that the velocity literally goes vertically. All right. So if I want to work out my velocity here, I'm going to differentiate that with time. Now I've used some funky deltas here. That's called a partial derivative. What that means is I'm going to treat everything else as a constant. So the spatially dependent bit, I don't care what that is. So let's differentiate. Then it's only the time dependent bit that I want. So that's going to be minus omega a sine pi n x on L, and cos goes to minus sine. Yeah, so that's where the minus sign comes from. So if I differentiate cos omega t, so let's just do that in the margin. Oops. So if I differentiate cos omega t, we'll do a bit of calculus today. So d cos omega t over dt, that's going to be minus omega sine omega t. We don't need the partials there, but there we go. All right. A bit of calculus knowledge. If that's new to you, excellent. Go and do some trigonometry. I'm going to be teaching my students in further maths in the lower sixth this very topic in the next week. So if you're on the call, hello. So there we go. So now we've got an expression for V, and what we want is the kinetic energy. So we can talk about the kinetic energy. So the kinetic energy is going to be a half mv squared. That's going to be a half times the mass times the square of this lot. So that's going to be a squared omega squared sine squared pi n x on L sine squared omega t. Okay, right. And now we're told that the kinetic energy and the potential energy are equal. All right, at all points in this wire. So therefore, we just need to double that to get our total energy. So since Ke equals Pe and E equals kinetic energy plus potential energy, this means our total energy, which I think is what we want. Is it the total energy or it's kinetic energy we want? Maximum kinetic energy. Right, okay, so ignore that for the moment. All right, so we just want that one. Okay, so I think I'm going to see if I can do this. All right, let's go and sort of have so you can see the whole thing. All right, I'm going to draw myself a nice vertical line here. Right, so I've now got a formula for the kinetic energy. Let's just put a little box in there. And what does it ask us to do for part I? The maximum kinetic energy along the wire between the range 0 to L. So there, oh, hello. Uh-oh. Something just crashed. Am I still broadcasting, guys? Oh, no, we're good.
Yeah.
Whew, that was close. Right, okay, so what we want. So we've got really a sine squared function now that we're plotting, okay? So your maximum kinetic energy is when sine omega t is 1. So when sine omega t equals 1, right? So we have a kinetic energy max. All right, so because of our formula here, let's just write that out at the top. So E is a half ma squared omega squared sine squared pi nx on L times sine squared omega t. So this bit we're going to assume is 1. That will vary with time. So a snapshot in time, we can then plot the kinetic energy. So that's if that's x along our wave, and that's L. Okay, if you look at our standing waves, I'll just put that over there. And this is our kinetic energy. Oops, we'll put that Ke. There's our kinetic energy. Let's call that Ke max. There we go. And so what have we got? Well, what are our various nodes? So let's have, and we're talking about the third harmonic, I think. Yes, the third harmonic standing wave. All right, so we need basically how many nodes have we got? Well, it's going to be 3, isn't it? So sorry, 4. So we've got 2 for the fundamental, 3 for the first overtone, second harmonic, and 4 for the this one. So let's just draw that one just underneath. So there we go. There's our wave. Okay, and that's our. So we've got another 2 there. There's something like this. That's a harmonic number of 3. And there's our sort of position at some point on this wave. All right, so what we've got nodes at the end, at L, and at 0, and we've got other nodes equally spaced like that. All right, and so our kinetic energy, because it's sine squared, is going to be going upwards. Let's have that in green. There we are, and there we are. So if you draw the nodes first, then you can have a good shout at making this symmetric. So what's the maximum? Well, the maximum, of course, when sine squared pi nx over L is 1. So max of 1. All right, and so our kinetic energy max, that's going to be half m a squared omega squared. There you go. And there's our position along the wire. So that's the first part. So what are we trying to do next? Let's have a little look. Calculate the frequency of vibration, drawing your line, the graph to show the total energy of the particles along the wire. We've done it. Brilliant. Calculate the frequency of vibration of the wire. Right, so now let's have a little look. We've got the speed of the wire, and we've got the tension and the mass per unit length. So now we've got to do a little bit of work to find all of those. So, okay, before I do that calculation, got any questions or queries from the chat? Or anything come out? Anything come out? Am I still broadcasting all right?
Yes, I'm just having a look. Uh,
I think it's pretty up to date, really.
Fantastic. All right. Okay. Well, interrupt me if there's anything that comes. So what we've got is we've got the wave speed is the square root of tension over mass per unit length. That's a really useful formula for waves on a string. Sorry. So that's wave speed. All right, and that's tension. All right, and that's mass per unit length. Okay. Right. What else do we know? Well, we know that speed is frequency times wavelength. What do we want to find? What are we asked to find? We're asked to find, I think, the frequency, don't we, of this thing? And remember, it's the third harmonic. So what else we're told? We've got, I think, the mass of the string, aren't we? So we've got mu. So again, like we started with in this sort of tutorial, we're like, well, let's write down what we know, and then let's just see how we get on for that. So I think these are our sort of three equations we've got. What else do we know? Well, we know that the mass is 6 grams, 6 times 10 to the minus 3 kilograms. What else do we know? Well, we know the length is 1.2 meters, I think, and the tension is 45 newtons. So if you're feeling a bit stuck, specifying what you know in a really clear way, it's probably going to get you some marks, I would have thought. I would give you some marks anyway. And we've got our amplitude, we're told, is 1.8 centimeters. So I'm putting everything into SI units here if I want things like energy, which is kind of helpful because that's the last bit. We want it in joules. Right, so what do I want? Well, I want the frequency out of this, so which is the speed divided by the wavelength. And I think we now got everything, haven't we? Apart from, no, we've got that. That's all good. So, so therefore, what have we got? We've got the frequency is the speed over the wavelength. Okay, and we've got, let's go and put that in. So we also know that the length, so if you think about it, it's going to be the third harmonic. Actually, there's an extra equation we've got. So 3 times lambda over 2, because this one is the third harmonic. Okay, so these are our things we need to put together. All right, so let's go and put that all together. So we've got some speed over lambda. So we don't need to work about what lambda is. So lambda would be 2L on 3. So we've got V over 2L on 3. That's all good, I think. Yes, 2L on 3. Good. So that's going to be, let's just tie that up at 3V over 2L. All right, now let's substitute for V. That's going to be 3 over 2L. And that's going to be the square root of T over mu. And mu is M over L. So that's going to be 3 over 2L, square root tension. And then we've got the mass over the length, nearly there. So therefore, we've got the frequency is 3 over 2, 1 over L. I might sort of put that into the square root. So 1 over L squared. And I've got T divided by M. And I've got an L here as well. It was a 1 over L. And that should be a nice way of writing it out. So 3 over 2. What have I got? Square root tension over the mass. And I've got L downstairs. Does that equal what I had last time? I'm just going to check my notes. Yeah, 3 over 2 root T on ML. So I think we've now got everything. So let's put those numbers in. So our frequency is 3 over 2. Square roots are 45. We're all in SI units, so that's what we want. 6 times 10 to the minus 3. And L is 1.2, and that's in hertz. And I make that 118.6, which is about 120 hertz. Let's just write that 118.6 hertz, which is about 120 hertz. Okay, can't remember how. I think we've got well, it's one or two significant figures here. So let's not over-egg the precision. Right. Okay, and now all we need to do is to find the total energy, and it's the average. So careful with this one. Let's just look at our question at the top. Good. So the total energy due to the vibration of the wire. So what we want to do is, well, we can look at our kinetic energy here. So now that's interesting actually. So do we want the total energy due to the vibration of the wire? So we're told total kinetic energy and elastic potential energy are equal. Of course, we're converting from one to the other. So you probably want the average of those. So let's go and have a little look and twice it. So I think what we could probably mean is that if we say just the kinetic energy, because they're shared, the maximum kinetic energy is going to be the total energy, all right, when the potential energy is essentially zero. So our maximum is going to be, sorry, our total energy is going to be our maximum kinetic energy, which is half ma squared omega squared. Yeah, I think that's what I got last time. Oops. So that's the one we want here. All right, so that's actually the total energy. Right, because energy is conserved in this system, so it's going to be the maximum. So half ma squared omega squared. Let's work that out. That's part 3, I think. All right. Oh, I think I've led into the next question, so I'm going to have to do another column. Sorry, I'm scrolling a bit here. Apologies. Right, here we are. So, so therefore, part 3. So our our total energy. Make that a bit bigger. Equals the maximum kinetic energy, right, which is going to be a half ma squared omega squared. That's a half ma squared 2 pi times the frequency squared. And if you put in all the numbers, now that's a half times, what was it, 6 times 10 to the minus 3. Amplitude squared is 1.8 centimeters times 10 to the minus 2. Don't forget to square it. And then in the bracket, we've got 2 pi, and I'll use my more accurate ones, which is 118.6 hertz squared. I think that's everything. And I make that 0.54 joules. So there we go. That's a rather nice end to the question. There's a few sort of like important things here, because you could get confused with things like the averages, etc. The total energy is the max kinetic energy. That's a really good thing to write. And then you could look at your diagram and your graph and go, aha, that's the thing I want. So I think that's a really good paradigm question, good revision of waves. We spent a bit of time on that one. Right, do we have any questions that come from this? Right, I don't really want to rush Q, which is the capacity question. So I might do that next week. So I'm wondering whether sort of like, hopefully my students won't roll their eyes here, because I did tell them I was going to do this one. But we might be better to do a slightly shorter one, which I think is H, which is an optics one. And then we've got a little bit of time to talk about the speed of light. So I think that'll be a fitting end. So we're going to just jump back. So I am going to scroll this one. So let's go to H. HI. There you go. Oops. Where are we? No, wrong way. There you go. I've got the right one, I think, here. There we are. Right. Okay. So here we are. And apparently this was a rarely done question. So the tricky bit about this, I think, is how to start. So what we've got a glass block, right? Sort of, it's a rectangular slab, but we've got kind of curves. So you kind of got like a sort of curvy rectangular block, nice sort of curvy, circularly curved ends stuck on a reflecting lower surface, all right? And we've got some light coming through it. And so the light ray, I'm going to make that red is here, okay? And it's coming out at this point. Right, so how is that going to work? Well, if you think about it, it's got to reflect off the middle. So we could have our rays that come like this, okay? Right, now it's a circle, so always we need to be drawing our normals. Okay, we've got a bit of geometry, haven't quite made that symmetric. Oops, this one needs to be going below. All right, it's a little bit of artistry required for optics. There you go. So there we are. That's my normal. And so let's call that θ1, and let's call that θ2, shall we? So that's my angle of incidence and angle of refraction. And by symmetry, you can see that that is θ1, and that is also θ2. Okay. Right. Let's call this something. So a quarter circle's a radius r. That's going to be that distance there. If you think about it, that's my quarter circle. If I can draw that down. All right. So that's also R here. Right, what else do we know? Okay, so this is glass. And we've got I'm going to call it in medium 2, so N2 is 1.46. All right, so now if you think about it, what we're trying to find is, well, we can do Snell's law, for example. We can do, so Snell, we can say that sort of n sine theta 2 is going to be 1.0 sine theta 1. All right, because we've got air at the top and glass here. So we're assuming this is air. Right, we don't care about the lower surface. Now, it's talking about if the depth of the block is 2 centimeters, what would be the minimum value of I to satisfy this situation here? And we're talking about, so I suppose, yes. So the situation we've got, what's the minimum value of L? So the idea is to kind of look at the critical angle. So in other words, if theta 1 was 90 degrees, and I'm looking at this side here, okay? So if that one was 90 degrees, it's coming out of the top. And so if it's coming out, that means it's a critical angle situation. I suppose alternatively, if my light ray hits the top of my sort of curvy bit, that's going to minimize L. So I suppose it's a little bit confusing to sort of say what this means, but that's kind of the only thing we've got. So let's just redraw that and just see if that makes any sense. All right, so let's see the situation like this, where that comes out. Oops, that's not symmetric. Apologies. Okay, here we go. So there we are. There's our quarter circles. Let's make that last one more like a quarter circle. And we've got our light coming in here, right, and coming out like that. Okay, so it's bounced in the middle, like there. Okay, there we go. Now, in this situation, that's a right angle. So if that is a right angle coming out, then if you think about it, that is our critical angle situation in ray optics. All right, so there we go. So what have we got? That's theta 1, and that's theta 1, and there's theta 2, which is theta c. So so when we have a critical angle, that's when, you know, I'll draw my my normal. No, that's fine. No, because our normal here, I guess that's probably what makes this hard. It doesn't seem like it's that situation, but if you think, because it's a curve, all right, at that point, I'm just sort of like talking about here, the ray is just coming out, and if theta 1 is bigger than 90 degrees, it's going back inside the block. So that's the biggest angle it can be. So in this situation, and of course we've got L being the distance between those two things. So if we were to draw that limiting case, and I think if you're like, well, how do I ask this situation? Well, let's take the situation where it is at the top. That clearly makes L smaller. What does that mean? That's probably your kind of logic in this situation. So there we go. If we've got theta 2 is bigger than theta critical, then that means we have total internal reflection, right? And in this situation, we've got n sine theta c is going to be 1 times sine of 90. Of course, that's 1. All right, so therefore, what have we got? It's got theta c is inverse sine of 1 over n. Which you put the numbers in, and that gives you inverse sine of 1 over 1.46, which is about 43 degrees. Pity it's not 42 degrees, but never mind. Okay, now let's have a look at it from geometry, what that means. Okay, so if this is the situation that minimizes L, which kind of makes sense. So this minimizes L. Whoops, wrong type of L, lowercase l. So the situation that minimizes L is the one where we've got a critical angle situation where theta 1 is 90. And then so we can use that to find out what L is. So let's do some geometry now. And all we need to do is the right kind of triangle. So let's have a look at maybe this bit here. So this one, if I just draw that in green. So that's L on 2. That's R. That's my critical angle. And so if we do tan, so tan of theta c is L on 2 divided by R. So L on 2R. And that means that L is going to be 2R tan theta C. Okay, and there we go. Now, what do we want to do? We want to work out what that is in terms of our equations here. It'd be quite nice to not have in terms of, I mean, we could just literally pop it in like this, because I think we're given R, aren't we? So what is R? Do we know that? Yeah, there we go. So the depth of the block is 2 centimeters. So that's R. So we're kind of done, actually. We could just go for, therefore, L min. Oops, that's not how we do it. L min. So if time is short, you could just do L2 times 2 centimeters times the tan of 43.2 degrees, which will give you 3.76 centimeters. Of course, you might want to write that not in terms of theta c. And what we can do is a bit of a trig identity. So just for a bit of extra, what we could say is, well, sine squared theta c plus cos squared theta c equals 1. And we want tan theta c. So if we divide this by everything by cos, so we've got tan squared theta c plus 1 equals 1 over, sorry, what am I doing? I'm doing the sine here. Apologies, other way around. So if I divide everything by sine, because that's what we've got n sine theta c, or sine theta c is 1 over n. So if we divide everything by sine, we've got 1 plus 1 over tan, because sine theta over cos theta is tan theta, and that's 1 over sine squared theta c. So what have we got? We've got 1 plus what we want, so 1 over tan squared theta c. Whoops, not a 9, a mysterious 9 has just appeared. Let's get rid of that. Let's get rid of this strange 9. Oh, that's odd. There we are. And that's going to be 1 over sine squared theta c. That's going to be n squared. So what have we got? We've got n squared minus 1. Divide that. So tan squared theta c is 1 over n squared minus 1. And therefore, tan theta c is 1 over the square root of n squared minus 1. So if we want a really nice formula, we've got the length is 2r over the square root of n squared minus 1. If you put in all the numbers, that will give you 3.76. So 2 times 2, which is 4, over 1.46 squared minus 1. That will give you 3.76. That's in centimeters. So there we go. Nice little optics question. So I suppose if you were coming to this like, well, what do I do next? Well, the only thing you can think about is the special case of critical angles. So in other words, this question is, well, if I minimize L, what else could theta 1 be? Well, 90 really. So that's how you would do it. All right. Okay. So we've got 5 minutes left. Do we have any other questions before I move on? No. Right. So in our last 5 minutes, we're going to return to the cosmic ladder, and we're going to have a look at how Ole Romer figured out the speed of light. So if you came last week, we were looking at the astronomical unit and how to work out that, and indeed the radius of the sun. So this is the sort of picture where we finished last week. So we found that the sun was 23,385 Earth radii away. And by looking at solar eclipses, sort of like, here's my moon here. If we know the radius of the moon and we know the distance of the moon to the Earth, we can do similar triangles, and then we can use that to the sun. Oh, hello?
Yeah.
Okay, I think we can hear you, Lena. Okay, anyway, so that's quite fun. So I'm going to skip ahead to rung number 4, which is lots of stuff about Kepler. So close your eyes. I think it's about here. There's lots on that section. Lots of funky things about orbits and Ptolemy. And then eventually here. So here we go. So this is Ole Romer, 1644 to 1710. And obviously at that time has an amazing wig. Or maybe it's his own hair, but I think it looks like a wig to me. And that's Christian Huygens, who looks a bit like a young rock star compared to Ole Romer. Favourable painting, 1629 to 1695. So they're kind of contemporaries. And I think a lot of the analysis of this was done by Huygens, but the measurements was done by Ole Romer. So what do they know? Well, this is all about Io and Jupiter. That's a kind of picture of Io, not to scale, but going around Jupiter. It's very sort of a volcanic moon squeezed by the kind of tidal effects of the gravity from its other moons like Ganymede. And that sort of squeezes Io to such an extent that it produces massive volcanism. So, all right, so this is sort of facts. What are the top trump facts about Io? It's about 421,000 kilometers about Jupiter, a period of about 1.769 days. And Jupiter's at 5.2 astronomical units and has a period of 11.86 years. We get that from Kepler 3. So what we do is we want to have a little look at this picture. So if I make that nice and big. So what we've got is we've got the Earth going around the sun. All right, and then we've got Jupiter going around a bigger circle here around the sun as well. And then what we want to look at is where Io, Jupiter, and the Earth are all aligned. So in other words, Io disappears behind Jupiter. So I'm going to call this sort of time where they're all aligned, the sort of like mid-occultation time. So an occultation is a lovely word, which is a kind of when a moon goes behind a planet. It's like eclipsed by the planet. So an occultation. And the mid-occultation time is obviously the bit sort of where, it's right in the middle of that. So what you can do is you can write out those times throughout the year when Jupiter occults Io. All right. So that's kind of the idea. So our sort of two sort of examples of this, of what we've got in this situation. And what you can do is you can sort of like work that out. Okay. So basically, this is the sort of like, so I've said Jupiter orbits more slowly than the Earth. That's the distance between Earth and Jupiter varies. That's a really nice calculation to do, by the way, is to work out the times and the Earth to Io distance. All right. So basically, depends on the sort of the Earth. So I think I've got some pictures here. So here we go. So we've got sort of the Earth and Jupiter orbit. And you can basically work out the times of the mid-occultation of Io by Jupiter as viewed by Earth. And you can work out the kind of time delay sort of for this. And what you've got, let's just sort of see what we've got. So you can basically work out, using Kepler's laws, the positions of the Earth, Jupiter, and Io, right? And you can work out the time between that and what you might predict for the Earth to Io distance. All right. So in other words, so if you were to have kind of time being kind of completely absolute here, so you run a little simulation. So the Earth and the Earth and Jupiter going around, right? And there's a little bit of a time delay from Io to Jupiter, but it will be kind of small. Most of the time is between Jupiter itself and Earth, and you can work out what it is as you go through the year. So I've sort of worked that into a little simulation. And these are your sort of model times, and you've got the kind of time delay. So in other words, if you were to sort of have a clock at the instant of Io and Jupiter in this occultation system, at that kind of absolute time, you can work out sort of where Jupiter and Earth is. You can work out how much time it takes for the light to get from, Jupiter to Earth. I mean, strictly Io to Earth. And Io is going to be sort of slightly above Jupiter, I suppose, for that to be seen. So you can basically work out how long it takes to get from Io to Earth at various points where you have this mid-occultation. And that time delay is going to change because when Earth and Jupiter are closest to each other, and when Jupiter and Earth are furthest away, that's going to be a difference of 2 times the astronomical unit. And that's actually a significant amount of time. So it's several thousand seconds, as you can sort of see on this graph here. So basically, what you can do is you can do the Earth to Io distance and the time delay, which you can work out of those mid-occultation times. You literally plot on a graph, and you have a delay of what you think it should be compared to actually when it happens. And if you plot those on a graph, you'll get a nice straight line. And essentially, the gradient of that is the speed of light, because you've got sort of distance is speed over time. So there we go. So if you work out those sort of distances here, so I'm using these numbers, my Earth to Io distance, so between 6 and 4.4 astronomical units. That's an astronomical unit, which we found last time. And you divide that by the gradient, so that the time here. So and that will give you about 3 times 10 to the 8. So there we go. So that's pretty darn cool. And so all to figure that out, you just need to take lots of measurements of exactly when your mid-occultation time is. And then you compare that to your sort of absolute model from Kepler's laws, work out the difference in those times. So our time delay would sort of move up and down on this graph. You need to do this carefully over many years, which is what early Roma did. And then if you basically know what an astronomical unit is, which we found last time, you can work out the speed of light, which is rather lovely. So there we are. I think that's something to have a look at. If you want to get this presentation, you can download it from the Eclecticon on the lectures page. So there we go. And well, there we are. I'll leave you with this. If you have this sort of orbit of Earth going around the Sun and Jupiter going around the Sun, draw a line between them, and you just sort of keep going, you get this picture, which is quite cool. So the blue line is the Earth, the red line is Jupiter, and you keep drawing these lines, you get this wonderful sort of multi-point star, which kind of is illustrative of the kind of ratios of the orbital periods, which by Kepler-3 is related to the ratio of the distances. So I hope that was fun, and lots to think about there. All right, thank you very much. Good luck with if you're doing ESATs and PATs and things like that. And of course, round 0, which I think is next week. So best of luck with that. We'll be back on Thursday. And then it won't be me over half term. It'll be someone else who'll be fantastic. And then we may or may not have another session. I can't remember. But very best of luck. See you next time. Thank you.